Okay, great. Won't take too long to do the intros because we are behind schedule here, but I'm really delighted to have Rick visit us. Rick is a chief scientist at US Ignite, and he has held, before that, he has been in part of many research labs and as well as founding some of them. He also has written books, he's got a lot of papers, he's an adjunct professor right now. He's an assistant professor, I think, at the University of British Columbia, I think. And then he's also one of the co-founders of the Planet Lab Consortium. He also has been pushing Genie from the very beginning. So with that, all yours. Thank you very much for your patience.
Oh, thank you for your patience. And you know, there was in the very early days of doing presentations from computers, there was a famous story. And actually, Apple featured in that, where you know, they're fumbling just as we were here to try and get the thing to display, and of course, you know, it was Apple ragging on Microsoft, and so somebody shouted out, people were shouting advice, just like everybody here was coming up to help. And thank you very much, by the way. Thank everybody for their help. And then somebody shouted from the audience, "Buy a Mac." So it turns out that's bad advice. Anyhow, so let's. So I'm going to just start something here, and we're going to try and do this live, which is not. And it looks like I can't do this because I don't have external SSH access. Oh well. Okay. So we won't do that, and instead we'll go to the presentation. This is Podium PC. There we are. Okay, cool. So I'm here to talk about the next internet, which is. Which I claim is a ubiquitous viral edge cloud. And to some extent, this is extremely self-serving because I've been doing edge clouds for forever. If you want to understand, so first of all, I have a contract. I have to put this in every talk. You should go to Springer and give them $150 for the Genie book, which I'm the principal editor. And have yet to receive any royalties, by the way. So by the way, if you want to flush a year of your life away for no reward at all, that's what you do. And the other thing is that, look, frankly, let's go build this thing together, right? I want you to help me to build it. I want you to define it. And I'd like to stand up front and take the credit and ideally do no work. I'm very good. Victor didn't point out in his introduction this. What I'm very good at. So there should have been more laughs at that. Come on, work with me. I know it's just after lunch. So there are basically 4 points to this talk. And given that we started late, and you probably know some of them, if this gets boring and gee, we know this stuff, move on. Yell, right? It won't offend me. So step one is to say, you know, what is an edge cloud? And in particular, how does it differ from something like Azure? Then secondly, why would somebody want such a thing? Which I know is something that Victor and I had a nice talk over lunch about this, and it's something that people at Microsoft are thinking about and struggling with. Well, not struggling with. I mean, it's something that we all see, and the question is why? How does it work? And then what do I see as the big scalability and interesting challenges here? Because I've been kind of fooling around in the space for 15 years. And during that time, have done what people who fool around in the space for a long time do, which is to say make lots and lots and lots of mistakes. And finally, making it a platform. And this is, and I had an interesting talk with Sharad today. I don't know if he was interested. I thought it was fantastic. And one of the points he made is that he was able to do his project, 3 guys, 3 years, I think he told me, in Azure, a really dramatic, because frankly of the capabilities of the Azure platform. So one of the things I'd like to do is say, suppose we had this edge cloud that goes everywhere, right? What do we do to make it a platform kind of like Azure, where you can just say, here, give me some search, give me a messaging platform, stuff like that. And I'm clicking too many boxes here. I'm clicking on the wrong one. So, you know, so what's the cloud? Well, the cloud is, you guys know, right? Better than me. You have a relatively small number of pops, but at each pop, right? And Dave Maltz from Microsoft quotes the size of a data center in megawatts. right? As in, I have a 100 megawatt data center with 30 milliseconds. I mean, big things, right? So basically, you can kind of scale arbitrarily, but only at a centralized location. And you have, I say no control. In fact, that's not true, right? You can say US East, US right there. You can pick a region, but you can't pick very finely within that. Conversely, at an edge cloud, right, or a micro data center, well, you know, there is no magic. You're gonna run out at a particular location pretty quick. But on the other hand, you got a whole bunch of locations, ideally within a few milliseconds of everywhere, with really tight control, obviously, over the location. You can put stuff where you want it.
What's the POP? What is a POP?
Point of presence. Sorry. Right. a place where you can put software. So if you then say, well, how does this work out? Well, really, the two sides are the flip sides of the coin. In an edge cloud, you know, you're going to have an application, it's got to have a whole bunch of components, but it's spread across a wide area. So you're going to have on the order of milliseconds to tenths of milliseconds of intercomponent latency, and probably on the order of a few megabits, maybe, of intercomponent bandwidth. But on the other hand, your bandwidth out to the edge, to the consumer, is going to be very high, probably on the order of a gigabit or so, depending upon exactly where you are. And your latency can be on the order of hundreds of microseconds to the very low millisecond range. On the other hand, if you're using a centralized cloud, it's exactly the reverse. Your intercomponent bandwidth is essentially arbitrary, or at least very, very high, and your latency is on the order of microseconds, right? And one of the Google engineers said, you know, we suck at microseconds, and that's the dominant latency. And that's the thing that really gets you when you start to do things like think about how do I really optimize the host networking stack? Because that actually becomes the dominant consideration for networking. I was talking to Amin Vedat, and we were talking about how he optimized the performance of Google. And of course, he won't tell me much. You know, like every third sentence was, I'm sorry, I can't tell you. But, you know, I did say, well, gee, are you using cut-through on the switches? He said, He said cut-through is noise. It's all in the end host stack. So you get very different engineering challenges when you're looking in the millisecond rather than a microsecond range. Boy, so the important thing is that there have been a bunch of these. It's interesting how you get these widows as you change boxes on doing this, right? So there have been a bunch of these that we built over the years. I mean, the granddaddy of them all was Planet Lab. It got up to about 750 sites. It's still nominally there because we don't say, when a site breaks, we don't take it off the list, we just say it's down for years. And what we gave you was containers on Linux servers. Genie, which we started to build in 2009, eventually got up to about 65 sites across the US. And there are two flavors of Genie racks. One is a 5-node rack. Most of them are Insta-Genie racks, which we designed at HP, which is a 5 to 10 node rack. And you nominally got a programmable network in between them. In fact, we never did that terribly well. And you could get VMs, bare metal, and containers. In fact, very few people actually got bare metal because with a 5-node rack, you don't have all that many to give away. Savi was a network of OpenStack clusters, 8 of them across Canada, relatively similar in terms of what you got to Genie. vNode, roughly the same thing. This was Aki Nakau's thing. GLab. So you're seeing roughly, if you look at all these things, and these are academic, right? So if you were doing this industrially, you'd probably, and you have more clients and people paying serious money, you boost certainly certainly these numbers up by an order of magnitude or maybe 2. Probably the form factor would be something like an HP pod. But in any case, that's still very small compared to a 200,000 server data center that you get at the standard cloud. A few NorNet is, come on, please. There we are. NorNet is something that's basically a Planet Lab clone, very very lightweight nodes to test multi-homing in Norway. Seattle, and the Genie experiment engine. Actually, so when I was demoing this, I was trying to demo this if I could have SSH'd in at the start of the talk. I'll talk a little bit more about this. This is a modern implementation of Planet Lab that Andy Bevere, Matt Hemmings, and I did over the past couple of years. And so this is offering Docker containers as a service across Genie, and now we have generalized it so that, and I'll be talking more about that later in the talk, so that actually we can plunk these things anywhere in the world very, very quickly. So Genie is an example, 60 POPs across the US, 5 to 10 worker nodes per POP, 80 to 150 cores, and we can put roughly 100 VMs, or probably on the close order of 1,000 containers on each of these things. And allegedly, we give you nationwide layer 2 paths. So we've been building these things roughly for about a decade, and this would be kind of typically what one would look like. In fact, if one were doing it industrially, various holes would not appear on the map, and so you get much better coverage, and you get better beef at each of these things. So now, really the important question is, what's it good for? And I'll be talking a little bit about that, and then we should have a demo that will actually work. So Matt, I hope you can hear me, and because it's going to be showtime fairly soon. And there's probably, whenever you do a new technology or a new infrastructure, you always get the value proposition wrong. You just do, because the real value proposition is in the applications that you can't imagine today that only emerge when the infrastructure is present and makes them possible. So this is an extrapolation from what we can do today, and what I see the value proposition as today. But I think that after we've had these things and people have been playing with them for 5 or 10 years, stuff that's much greater is going to emerge. So the two big things are latency and bandwidth. The cloud is great, but it's too far away. And this group, in particular, Victor and his group, have been pioneers in saying, these are the kinds of things that you can't do that you can't do on a standard cloud, just because the latencies will kill you. And I'll show an example of that in a few minutes, an example of a live app in a few minutes. The other one is just data volumes are too big to handle over the network. And I'll go into this a little bit. But fundamentally, our ability to store, collect, and process data is greatly outstripping our ability to send it around. There's some quantities to that. And so ultimately, you say, well, we just can't lay any more glass. Laying glass is just an expensive proposition, and ultimately, it's a lot cheaper to plunk computers down where you need them, as opposed to putting glass in the ground. So this gives you 4 broad classes of application. One is bandwidth conservation, right? Locally replicated computation over disparate data sets, where you just, with various forms of caching, I mean, this is basically the granddaddy of all of this, is content distribution networks. The second is a new class of application, which I call cloud in the loop. I mean, if you think about cloud applications today sitting on Azure, you're talking fundamentally about batch or at least very low latency applications, right? Even stuff like Office 365, right, where you're getting this collaborative editing capability. In fact, the data volumes are so small that you're interacting locally with your browser, right? And the stuff and the actual interaction with other people is on a much longer range basis, on the order of seconds to minutes. So we don't really have a true cloud in the loop processing. We have browser in the loop processing backed up by the cache. But if you want to do things like control of an IoT device, for example, that isn't going to cut it. Or if you simply have too much data for the browser, that's not going to cut it either. Gateways are, I think, very important. And the classic example I use for this is the baby cam attack last October, right? Anybody remember that when DNS got trashed? So okay, so I saw somebody shaking his head, right? So briefly, for people who don't remember the incident, there was a virus on baby cams that went off and flooded DNS with DNS queries, and kaboom, right? Because lots of baby cams out there. Stop. Why exactly does a baby cam need to make a DNS request? What's it going to do?
It's getting a software update from server.
What's that?
It's getting a software update. It needs to connect,
Yeah, the point is there's a limited connectivity capability that a baby cam has. Doesn't need the full network stack. So an alternative architecture is to say, well, look, I'm going to stick a gateway between the device and the network. The device gets to talk to the gateway talks to the network. Right, so a generalized gateway is, so this protects the people, so this protects the network from the devices. It also protects the devices from the network, right? If you're controlling your nuclear power plant over the internet, you probably want something sitting in the middle, just making sure that everything's okay. And in the fourth case is truly distributed services. Network mapping is probably the canonical example of that. Okay, so I'm going to show you an example now of a cloud in the loop application. And so the setup for this is, this is a guy at Telecom Italia who saw me demo this, and he said, this is the Google Docs. You invented the Google Docs for visualization. Briefly, I had to do a demo a couple of years ago for why Genie was valuable, and so we womped this up. A guy named David Larry at the University of Texas Dallas has a pollution data set. Can show you pollution values on a 10-kilometer grid worldwide, which every month between September 1997 and January 2015, however many years, a couple of hundred months, I guess, roughly, more or less. And we've got about 2 million points per month and an 11 gigabyte data set. And so the constraints we had on this were, one, any device, right? So usually when I'm not traveling, which I guess I'm always traveling, I actually do this on a Chromebook. So I can't cite the data on a Chromebook. I can't cite it on a phone. I can't cite it on an iPad. I can't cite it. Any of these really thin devices are too thin to take the data. I wanted to render it through a browser. I wanted it to be truly interactive, and I wanted it to so that I move the mouse and it clicks. And then when we put it and I wanted to make it collaborative anywhere in the world. So in fact, if you move the mouse in Washington, so if you were sitting in Tokyo and I were sitting in Washington, you move the mouse, I'd see it. And with luck, assuming that everything is working, well, we'll get to that right now. So here's a screenshot. And rather than a screenshot, let's go off and see if I can get my laptop up. And Matt, if you're there, it is going to be, as soon as I pull the right window up, it's showtime. So here we are. And there's Matt. So I have two. So Matt is my collaborator, my former student. Now he's graduated. My collaborator on this. So now you can see the data set. We're looking at July of 2002. This, as you can see, is a browser. So we're using standard browser software for this. This is polymaps.js running on just running on Chrome. It's kind of a neat tool that we use to throw this page together. It's one of my favorites. But as you can see, I can zoom in like this, right? And even though that actually, I'm looking at a pre-rendered data set. But if I just hit the month and went from September to August, you can see that this involved loading an entirely new data set. And you can see that was completely smooth and completely interactive. And no, I didn't cheat and preload anything, right? And the reason is that if you take a look at the URL bar up here, I'm talking to the University of Washington. So that's just going across town to fetch this. And I'll give you some statistics on this. Let's go off and advance the year. But once we did that, sorry, 2004. Hey, Matt, if you can hear me, can you do something, please? Matt? There we are. So Matt doesn't see quite. Oh, yeah. So what Matt did was he changed the value on the on how we're displaying this, so that to rescaled stuff, so that this looks a little bit less polluted. Actually, Matt, pan the map if you can, please, if you can hear me. And as Matt, so you can see Matt is sitting at his apartment in Victoria, and as he does stuff, I can see it, right? And as he does stuff, I can see it. Now this, by the way, you know, you can do this with video games, right? You can be playing a game with your buddy in wherever, and by and large, you know, he shoots you and you die. You know, you feel it. Ideally, you shoot him and he dies. But that requires a fat client. So what we're seeing is that two people sitting just in front of a browser can interact with a rich data application and each other across the world. And the reason it works like this is that when I change the map, all I'm doing is I'm sending a small status to Matt with this information, the view box that we're looking at, and that's pretty much it. Maybe a few, so it's a few tens of bytes. That's what goes over the wire. His browser sees it and sees that I did it, flashes up a RIC sign, and then goes off to the server and fetches it from there. So it's exactly as if he did it. So this is an entirely new capability, not because we're brilliant. I mean, you can see Matt and I lumped up this page. Believe me, anyone in this room, I'm sure, could do far better. Neither of us are terribly proud of this, are terribly proud of our artistic ability.
Are you using like a web socket for Matt and you to communicate with each other?
Yes, and that's a sore point, by the way. The messaging server that we're actually talking to. The messages, two things about that. One is the messages actually go through livelyweb.org in Fremont, which is ridiculous. So one of the many things on my to-do list is replacing that with a Kademlia-based peer-to-peer system. Which is going to be A, more robust, and B, solve the round trip. But yeah, it's WebSocket-based communication. Did I see another hand go up?
No, just...
Okay, great. Matt, thank you. And by the way, the add node didn't work, so we're going to, so we're done demoing, but feel free to hang around. And thank you, Matt. So you saw the example. Okay, so just to recap, by the way, the browser takes 100 milliseconds for the browser to draw. So that's dead time, right? So we have 150 milliseconds end to end. I really beat up on the wire on the data set here and did a new wire product. Basically, there was a lot here to optimize the wire, but even so, it was about 30 kilobytes per transaction. And in order to pull that across, I'm looking roughly at 2.5 round trips. I said 20 milliseconds, and also really optimize the server to make this work. In fact, it had better be closer than 10 for this to really work and be as optimized as you saw it. So that's an example of something that simply can't be done without an edge cloud, because if you want this to work for a user anywhere, that means you have to have a cloud within 10 milliseconds of everywhere. And I think this is the tip of the iceberg on the kinds of applications that you're going to see and require, right? I mean, this was something that a couple of guys could womp up out of available data. But things like other applications in this space include streamed VR to mobile devices, where you want to be able to, where in that case it's actually a latency thing. You want to have the server that's doing the rendering and putting out the HTML streams to be sitting on a local area network with the clients, because there's no way that you're going to push that out over the wide area. So so this works across continents. And by the way, I demoed this. So I'm working with a bunch of radio astronomers. If the NSF grant comes through. These guys are doing, are looking at pulsar data and what they're looking for is gravitational waves, right? And so that what they want is two things. They want a CDM to distribute their data repo around the world, because they say, if we find a gravitational wave, we're going to die. Because everybody, his brother, is going to be hitting their repo at Cornell in West Virginia. But the second thing is they also want to be able to use a capability like this using Jupyter notebooks, which is their primary tool in communication, so that they can communicate. Right? They just put together a new array in South Africa, and basically a radio astronomer sitting at Caltech wants to be able to interact in real time on a data set with a radio astronomer in South Africa. So I showed this to them, and the guy at NASA said, his eyes popped out. He said, "Can you make this work to South Africa?" If you've got a server in South Africa, yeah. I mean, the bandwidth requirements are trivial. So we did this, and this was like 3 o'clock in the afternoon in Washington. So these guys were saints to stay up in the middle of the night to work with us and to work with us. And so sure enough, we did it. However many 8 people, 6 countries, 4 continents. And we all saw the same response that you saw right there. When you've got a room full of congressional staff, that's another one. So this is, I mentioned the gateway. Another good example. This is John Kubiatowicz and his colleagues at UC Berkeley. It's the global data plane. This is a network of write-once logs. So they, and the idea is that if you've got an IoT device and you want to get the take from it, it writes to a log, you read from the log. So the idea is that you decouple the IoT device and the applications that talk to it and work with it. And you can replicate the logs. Their idea is that this is primarily used for scalability. I also claim it's a way that you actually secure the Internet of Things by doing stuff like that. So this, I think, is an exemplar of another thing that's going to require high distribution, because you'd really like low latency from the local GDP node to this. And then there's this lab in Redmond that came up with this thing called cloudlets. You guys might have heard of these things. Satya keeps talking about it. But these guys, if you go off, and I mostly know about these things from Satya's webpage, where he's been talking about doing this. But he's identified things like disaster relief, where you just pop these things in where there's a disaster. And US Ignite, by the way, we look at public service applications. One of the things I'd like to do is put one of these things in the back of a fire truck, right? So that we can provide firemen data when they go running into a burning building. Yeah, go on.
What is soft state?
Soft state? Actually, the embedder of cloudlets is sitting right here. You want to answer that, or you want me to?
You should do it. I want to see how
No, so soft state. So basically, soft state is state that is cached from elsewhere in the cloud, or that pushes up very quickly in the cloud. The important thing to understand. I mean, why do people go to the cloud? Well, people go to the cloud to kill OpEx, because maintaining computers are expensive. Maintaining computers are not expensive, right? This is what's expensive and difficult is maintaining state. When they go off to when they announce on the airplane that, if there's in the event of emergency, leave your stuff behind, no way. Let me tell you, I'll die before that thing dies, right? On the other hand, my Chromebook, I mean, I'll throw it under the bus. What do I care? There's nothing there. To a certain extent, the same thing is true of my phone, right? I mean, this thing can, and so if you're talking about a little micro data center sitting back in the office, if that thing doesn't have any hard state in it, it blows out. What do you care, right? How much are you going to spend maintaining that? You're not going to have some guy sitting 24/7 praying over the thing to keep it going, right? So that's what's expensive. So the important thing is that you can retain the benefits of having local computation, which is to say low latency and high bandwidth, and probably other things. Low latency and bandwidth are what I can see today, if you don't have, if all you've got on it is soft state. And it's been a tremendous insight that's been, as I said, largely due to the people who are sitting in front of me. Which is why it's lots of fun to tell you guys all these things that, believe me, you know better than I do. 5G wireless, right? So 1,000x bandwidth increase and 100x latency reduction. The billboard stuff about 5G. Wait a minute. What miraculous radios are actually going to do that? And the answer is, come on. The only way, I've actually done a couple of times in my career, actually improve the performance of something by those kinds of numbers, right? And so I can speak to this with some experience. The only way that you get those kinds of improvements is if you're fixing something that's terminally broken, right? And what you do is you make it kind of sort of work, and then, well, that's a tremendous improvement over the state of the art. But it's still lousy, right? So what's going on here is the radios aren't terminally broken, right? You've had a lot of really good guys who have worked on this for a long time. They've got coding down to the information limit. They've got the electronics doing well. I mean, the radios are really good. So the only way you get that is to change the architecture. And in this case, changing the architecture means that you're putting the computation right next to the base station. That's how you do it, really. And so this, again, is another case where people are basically doing an edge cloud. So another one, everybody's least favorite example is telco COs. Now, this is being done. The telcos are coming at this from another direction entirely, which is that their COs are just filled with these siloed appliances that do stuff. And actually, if you ask them what stuff they do, it sort of gets vague because, well, we've kind of grown this appliance over the years. And it's like anything that you grow over the years, it's gotten big and crusty and awful, and nobody actually understands it. So their idea is, oh gosh, we're going to fix this and really reduce our CapEx and OpEx if we take these siloed appliances and we turn them into a bunch of virtual machines running software, which is basically, if you pry open the appliance, what they actually are. But my guess is, or my claim here, and I have no information that they're actually going to do this, even though they're thinking about this for their internal functions, at some point, even somebody like a telco executive is going to realize, hey, we have all these computers sitting around the United States that we really don't use most of the time. I'll bet we could sell time on them. I'll bet you can. So they'll open it up to other services. It'll take them a while to do this. Now let's talk a little bit about bandwidth. And there are numbers here, but briefly, the bottom line is take a look at this thing, right? This thing is improving an awful lot faster than the network which carries its take. Actually, this morning I had to upload. I got a bogus parking ticket yesterday downtown, and so I took a photo of it. I had to appeal it, so I took a photo of it on my phone. And then, the only reasonable way to transfer it to my phone back up to my computer was by email, which and it took forever just to get just to send the damn email to do this. So this is so this is happening, right? Our ability to store, capture, and process data is greatly exceeding this. And actually, it's easy to show. There's a back of the envelope calculation that if you take any city, including Redmond, Washington, and say, how much what's the ratio of the cross-section bandwidth in the city to the ingress and egress bandwidth, right? And the answer is it's going to be like 100 to 1 or more. Right? I mean, that's, the only skills required here are multiplication and division. Oh yes, and guessing what the telcos have in capacity, which they won't tell you, but you can pretty much guess pretty well. And the answer is it's orders of magnitude. And this is because if you actually take a look at the price performance of computation and communication, this is megabits per second at peering points, this is gigaflops. And it's normalized so that the 1997 cost was 100. Now, the blue curve is computation. You can see it's much less than a tenth of a cent. if that's $100. This is something less than a dime, right? So both of them have improved dramatically over the years, but this is a doubling curve of 11 months. This is a doubling curve of 18 months. This is a doubling curve of 11 months. And what that means is that the ratio, and the ratio is what counts, has changed by 3 orders of magnitude. So computation, our ability to store, process, and capture data, has outstripped our ability to send it around by 3 orders of magnitude over 18 years. And what this means is that the network architecture and the cloud architecture has to fundamentally change. I mean, you can't take a 3 order of magnitude ratio change and say, oh, we're going to do things the same old way, right? And it never flies, right? So traditionally, I mean, when the internet was embedded or evolved, or did whatever it was it did, right? I mean, you lived in an era where computation was expensive relative to communication, and now it's nuts, right? It's just stone nuts. If I went to the University of Washington and said, hey, can I download a 10 gigabyte file from some server? Oh yeah, sure, no problem. We'll stick it on the website, or we'll stick it on the FTP site, whatever it was. Any professor can put up anything of whatever size and say, here, go download it, and nobody cares. If I go and say, hey, how about you give me a VM? Oh my God, this is precious stuff. What, you want my firstborn too? It's crazy. We are giving away what is expensive and hoarding what is cheap. And that's our network. That's the network and the cloud architecture we have to. Now, mostly this is a social change we have to have. We have to be able to say, yes, it's okay with us if you run programs on our computers, and that's a change in mindset too. But also it means that we have to rethink how we want to use the network. Instead of sending data to people and programs, we want to send programs to people and data, right? We want to be able to send the stuff that renders for you right next to you. We want to be able to send the program that processes the take from your telescope, your sensor, your whatever. We want to send it right next to that and run it there and send only the take back. Only the take from the sensor back. Okay. So, oh man, we're running late. So so the next question is, okay, so if you buy what an edge cloud is, if you buy that there's actually use for these beasts, and if you buy that it has to be everywhere, then the next question is, okay, how do you make it happen that thing lives everywhere? And the answer is, well, we've actually done this twice. Right? Did it with the internet, did it with the web. And so we can tell you something about successful infrastructures, which is they live off the land. This is the single biggest mistake I made when we did Planet Lab and when we did Genie, right? And you would think that after doing it once, I'd have been bright enough to realize, don't do that again. I'm stupid, maybe third time lucky. Right? So successful infrastructures use local resources. And they spread by local action, which is to say, you say, hey, I'd like to host an edge cloud node. Great. Download some software, run it, and off you go. Right? So just software download and configuration. So, the internet used existing computers and phone lines, right? You ran Berkeley Unix, you hooked it up to whatever your existing communication service was, and presto, you were on the internet back in the 80s. The web just used the existing internet and services. I mean, it was an overlay over FTP, first of all. And a 9-line shell script was the first web server, but anybody could be a website back in those days. Jerry Yang did the original Yahoo on the Sun workstation in his office, right? And so that was how this stuff really lived, right? You could put up a web page just with BI and with VI, and then you download the server, and presto, you were on the internet. So that's actually how you spread. And so here we've got the viral edge cloud. And the demo that the other demo I wanted to do today was, well, actually, let me flip to the other, flip back to the laptop, because I have the web page up. So we built this thing called Planet Ignite. It's based on Genie Experiment Engine. Here's the set of nodes that we've got right now. The idea was to make Genie very easy to use, so I can get a slicelet, which the Genie people objected to me calling it a slice. I'll just go ahead and click on that. Whoops, no, I don't want a custom slicelet, you idiot, Rick. I've got to get where I ask for ports. So now I've got ahead, and it's in state processing. When it comes up, I'll be able, which will be in about 5 minutes. It used to be instantaneous, but then I put in the delay because when I had a class full of people doing it, and it crashed the server. So now we actually put things in one at a time. But so this will change from processing to running in a couple of minutes. I'm also an admin, so I can look at the admin dashboard. A couple of so there are 3 slices that are up and running right now, and nodes. And actually, what I was trying to do at the start of the lecture, but I couldn't get an outbound SSH port, is I had a shell window open on a node in Cornell, and there's about a 40-line shell script that you can download, which I had downloaded. And all I had to do was run it, and by now, had I been able to log in and do that, we would have seen that Cornell would have been on Planet Ignite running. So I literally have brought nodes onto this thing in 15 minutes, just running a shell script, and actually the next version of this, I'll just prep a VM image and bring it up. Cassini, by the way, I showed this to the Planet Lab Europe guys. Cassini is the name that Timur Friedman picked for his personal laptop over in Paris. So this is actually a MacBook Pro. Most of these things are Genie nodes. This is a Savi node. Ubiquitous is a Savi node. This is just a VM that Justin Kappas has. Anyway, so I can then, oh, all right, I'll fix that. I just re-brought up the portal, and probably what happened was, never mind. Anyhow, had it worked, I could then download the slicelet file, which gives me a tarball, everything that I need to run the distributed job. And then I can actually run Hello World across this thing in my, just from an SSH window on my desktop, which using nothing but the configuration stuff that we threw there. So the idea is to do it like that, to just provide an image that you can download, put on your Mac. Well, your MacBook is excessive, but put on your MacBook, put on your home PC, put on whatever, and federate with this edge cloud, and then let people run jobs inside slicelets. So this will make the edge cloud viral and downloadable, and this makes adoption trivial. Right now, a Genie rack, which is the state of the art, costs, I figure, about 50 to 70K a year in OpEx and CapEx costs. We use custom tools. There was an initiative a few years ago called Bring Your Own Rack, which was to dedicate existing equipment to Genie. And it's better because you just downloaded the software, but the software tools were largely commodity and well supported, so this was better, but you still had to dedicate the rack to Genie. But now we want to take it one step further, and there are 2 levels here. The first, I'll skip over this because I want to get to the last stuff too, and we're now at where the end of the we're now getting close to what should have been the end of the talk. But right now, actually, if I take a look at using Genie, which is this thing, we have rack managers, which are, you can think of these things as basically roll your own OpenStacks or Kubernetes, right? Because they were done pre all that stuff. And then we have a bunch of global tools that go off and make requests to these things. But the interesting thing is that if you take a look at any rack, or any cloud, whether it's Azure or a local cloud at an institution, I mean, they're used to having tenants go off and make requests, right? Basically, that's who makes requests, right? Just some, whether it's Chef or Puppet or Ansible. I mean, there's some user tool that makes a request. The user rarely goes off to the GUI and allocates stuff on a VM by VM basis. So hey, instead of these guys talking directly to the rack manager, let's have them talk directly to a user tool tenant, which will then go off and make requests like this. Now look, almost any institution will be running its own cloud for its own resources, and most of them will have free capacity. So I can go back and say, well, hey, look, just give me, you don't need to dedicate a rack. You don't need to dedicate a guy. You don't need special purpose equipment. You don't need special purpose software. Just, let me run on your existing cloud. Hand me some VMs, and if you run out of capacity, cut me off. All I really want is the excess capacity here. So and I know this will work because this was basically how we federated Genie, which is the American federation, with Savi, which is the Canadian thing, which was a network of OpenStack things. Me and my students at the University of Victoria just modified the back end of one of the Genie tools to talk to OpenStack as a client, and it worked just fine. Planet Ignite I showed you earlier. It's just that was the infrastructure I showed you earlier. This is Genie as a service light. Instead of, if you don't have a cloud, great. Everybody's got a VM. Just download this. Install it on your whatever, right? Your Windows box, your Windows box running. I will have a Windows solution. Right now it's all Unix based. Let me federate with me and let me run stuff. Right? And we don't get, with Genie, we got all this networking. Don't get that with this. But, Genie, but Planet Lab, and this is just basically a viral version of Planet Lab, was a very, very useful computational infrastructure for a long, long time. So that's a G. It was a modern implementation of Planet Lab, which was embedded in Genie. Planet Ignite is the viral version of that. Planet Lab was LXC, eventually it became LXC containers on bare metal. Planet Ignite is Docker containers sitting in VMs. And in both cases, the slice is just a network of containers spread over wherever. So we made it downloadable. And I tried to demo that for you before. But this is basically unfunded now. So it's me, Matt, and occasionally a little bit of Andy, just maintaining things part-time. We had a borrowed rack at Stanford for our portal. It crashed. I just brought up the new portal, so it's which is why I got an error. There was probably a key problem doing the download. So it's suffering from not a lot of tender, loving care, but it's okay. We've got a bunch of sites that we've brought up. Mostly as a demonstrator. We need features, and there's a bunch of features and scalability, which I would love to add if I ever get the ability and funding to do it, that we can maybe talk a little bit about at some point. So, okay, what's making it a platform? Well, every edge cloud I've talked about so far has had some assembly required, right? I mean, if you ever use Genie, or if you ever use Planet Lab, what we give you, basically, is here. Have some containers. If we're really lucky, it'll give you a network between them, and some IP addresses, and go to it. Well, that's kind of the equivalent of giving you a bare metal computer, and saying. Here, go to it. And in fact, that's not the way we write code these days, right? I have this on your personal laptop. You've got a whole bunch of utilities and libraries that other people wrote. People had nothing to do with building the computer. People had nothing to do with building the operating system. They just contributed. You installed it with apt-get or whatever. When Sherrod was building his service, he was telling me, I didn't build my own search engine, right? I just used Elasticsearch. So these. So the idea is that what we want to do is build a software infrastructure so that people can do the same thing here, build globally distributed services. So we're building this on top of XOS, which is an operating system to instantiate and compose containers. The current XOS is designed by Larry Peterson, currently at the Open Networking Lab. You will also hear me call this, on the next few slides, interchangeably Cord. WorldOS is the extension that we're building now to extend this to the wide area, so it goes across multiple sites. And it's a joint project of US Ignite and ON Lab, which is the core consortium. If you take a look at what we did for the visualizer, well, there was this data repository that we replicated across sites by hand. I had to pick which site to talk to as a client by hand. I had to write this messaging layer, again, by hand. And actually, we borrowed one that was built at the Lively Web, but we would have had to have written it by hand. So there was an awful lot of hand stuff there. And a lot of this are global services. For example, there should be a standard messaging bus that lives between sites that I can just use without having to write my own. There is absolutely nothing about a file system that says it has to live in a single computer, a single disk pack, a single data center, or anything, right? It's just a logical collection of stuff. So there needs to be a wide area version of a file system that these guys just subscribe to. And I need to have a global redirector that says, look, I just want to take a look at the pollution data, right? It sees where I am, hydrates a node near to me, if that needs to be the case, brings it up and seamlessly redirects me to that without me as a user even knowing. And if that node craps out, and they do, right? Large infrastructures have this property that some percentage of them are failed at any one moment. Well, pops me seamlessly over to the next node, ideally without me noticing. So if you take a look at a classic cloud now, even something like OpenStack, which sucks, right? What you get is a whole ton of services. And then if you take a look at current Genie, right, and say, well, which of these services do we have the equivalent of? Basically like the foundational floor, right? Got some networks, so got a little, we can store some images, we can allocate stuff for you, and we can authenticate kind of, sort of. Can we orchestrate? No. How about a distributed file system, block storage, object storage, a distributed database, analytics engine, monitoring and telemetry? No. Don't have any of that stuff. Software's there. People are writing it. So what we really need is a way to package all of that and stick it into NextGenie. So how do you do this? Well, the first thing is you don't touch what's really there. And instead you do it as a layered architecture. In Planet Lab, whenever we were asked to add features to Planet Lab, and we were, right, constantly, we need you to do X, Y, Z. Oh yeah, why do you need us to do that? Well, it's important that we have, well, let's say distributing software to the nodes. Okay, can you do that? Yeah, I know how to do that. Okay, do it. Put it in a slice, right? You don't actually need to put all this stuff into the kernel. Almost all the stuff that the operating system on that laptop does for me doesn't sit in the kernel, wasn't written by Apple, right? It's just utilities that was written by somebody else, and what Apple actually provides is a way to find and instantiate those things. So we said put it in a slice, and the next thing we're going to say make it a service, and the service lives in a slice. So XOS, which is also called Cord, is basically this orchestration engine for services. What's a service? It's a bunch of containers running some software, right? And you say, Docker. You basically say, here is my Docker file, and then a little orchestration magic on top of it. Go instantiate this. It also has a composition. It also, and the idea is it was done for telcos, but it fits beautifully into this. And moreover, if I adopt something that the telcos are already using, well, gosh, that's going to make it fairly easy for me to turn their central offices into a general purpose edge cloud. So basically, all it takes is, the The software that forms the service, that's written entirely independently of the horsepower it takes to instantiate it. So you write a small service description, a small synchronizer, which is just basically how do you load up the containers and how do you instantiate them. Cord takes that, it takes a service request, generates all that, or gets some containers from the cloud manager, and it hands you back a service instance, which is the containers running what it is you want. So World OS is our multi-site version of this. The prototype that we're building with Verizon, the Open Networking Lab, Matt at the University of Victoria, and me, is something called hierarchical cord, and which is to say we take a cord, this XOS, which understands how to instantiate services on a local box, and turn it into something that can do it on a bunch of clouds, right? Here's the picture, right? Global cord talks to all the local cords and say instantiate services. So in fact, it just really replace the manager here with the local cord. So instead of saying, here, go load this software in all these containers, say, here, hand me a local instance of this service and the connectivity information that talks to it. Going back to the visualizer, again, what does it take to make it work? Well, basically, I outlined this, right? I need an intercomponent messaging system, I need the file system, I needed a redirector, and all that stuff. And all that stuff, if it's in orange here, is something that should be provided by global services. So what I have to write is essentially just the web page. And maybe the data server that takes in a request goes off and fetches something from the local file system and squirts it out on the wire. Maybe not even that. And this leads to a bunch. So if you buy all of this, then hey, look, there's a whole bunch of stuff that needs to happen, right? Building this global operating system. How do we and Planet Ignite is a toy. I've put it up to a few. At best we were up to a few tens of sites. I'd like that thing to be at tens of thousands of sites. Justin Kappas called Seattle Million Node Genie. Really like that. But when we scale this thing, that's going to be a fantastic overload of what we could do, and so how we handle all that. Dealing with the cap theorem when there are latencies of greater than or equal to 50 milliseconds between components, right? That's not something that people have really had to tackle yet. Trust and security in a viral computational environment where nobody can trust anybody else, because you don't have a single administrative domain. You're running on computers that are basically owned by somebody anonymous. How exactly do we arrange for trust and security? We did have issues with that when we were doing Planet Lab, which topped out at 750 sites and thousands of nodes. So, of course, everybody's greatly relieved to see this slide in any talk. You don't have to agree with that, right? So Genie's already an edge computing infrastructure, small one. Next Genie is going to be Genie, but viral and based on persistent distributed services, so that people can write large-scale services like the one I showed you, and it shouldn't take 3 months, most of which is building all that infrastructure, but a few days using this World OS thing, and of course. Building all of this, a viral computational infrastructure, a services layer over it, this is a truly enormous job. So the audience rather than me should specify the services. So audience rather than me should tell me what it takes to host. Audience rather than me should tell me what it takes to do an edge cloud. And as you can tell, of course, I have very little to do with all of this stuff. I have a tremendous number of collaborators, and thanks to them all. And that is always the last non-pretty slide, and here's the pretty slide. So there you go. That's the end of the talk. I should have pulled the Jeb Bush and said, "Please applaud."
He said that. Okay. Any questions? Any thoughts? Comments? Yeah. Any thoughts, comments, questions, everything is all here, so go for it.
Yeah, I have a question. Like, I think, from my perspective, the hard part is mixing persistent state with this idea of, an edge cloud across nodes where, you mentioned like when you have lots of nodes involved in a system, some amount of them are going up and down, are failing.
exactly.
And so like, do you have thoughts on, like if you can get one of these edge nodes like close to the user, you can get very short round trip times to it. But if that node then has to, persist that data not just on its own, not just on its own machine, but to other machines, like, how much does that actually help, I guess?
Well, I mean, it depends upon, well, so first of all, it's a good question. But rather like, there's a slash in TCP IP for a reason. And it's because not every network transaction needed in order reliable transmission, right? So you deliberately, so handling that was a policy question for the transport protocol rather than the networking protocol. And I think the same thing is true here. Like with the visualizer had read-only data, right? I mean, we're looking at data, not manipulating it. So for that, if a node crapped out, who cared, right? You just fail over to another one. You can also imagine the case where, or another very large class of example is where data is updated, but if you lose the updates, it isn't a tragedy. I mean, or if the updates are out of order, it isn't a tragedy. I mean, a good example of that is Facebook, right? This is why your feed, you see these out of order events in your feed, right? It used to be the case that, I would get email from Facebook saying that, so-and-so had commented on my thread, and I'd look at the thread and it wasn't there. This was just because they didn't have any idea for an atomic transaction. eBay, right, has a huge problem because they've got to run a two-phase commit over the wide area, right? If you're doing transactions, you don't have that luxury. So this is an example where basically it's going to take the application layer to do it. But what the infrastructure needs to provide, just as in a networking case, you provided a variety of transport protocols with different properties and guarantees, and the performance hits that come with that. You're going to see the same sort of thing here, right? And mostly in the cases that you're thinking about, I think those are probably going to show up at the database layer, right? You're going to get essentially the equivalent of a wide area Cassandra, which is going to be out of order, but so what? And then you may find things which are partition tolerant and retain relatively high performance. So a good example of this, and I'm not sure if he's actually published it yet, is Gun Sierra's idea of a witness database, which will have much higher performance than a blockchain, but will offer many of the guarantees of a blockchain. Fewer and weaker, right? Because there is no magic, but still sufficient for many purposes. In particular, it will probably be sufficient for smart contracts, right? Though not for money. Does that respond?
I think so. Yeah.
What is the latency or average latency you get down to if you bring the edge cloud down to the COs, thousands of COs that are distributed across the globe? I understand the big cloud's too far away, but when you come down to the actual central offices, how far are they typically away from the consumer that's trying to use it?
There's 4,800 in the U.S., and that means that you'll typically find one in every medium-sized town or larger. So my guess is that if you're in a truly rural area, you're out on a farm or something, you're probably looking at the 10 millisecond or so range, or maybe beyond. But if you're in town, it should be in the microsecond or low millisecond range.
And just to follow on to that, for the sets of scenarios you were describing, especially around IoTs and so on and so forth, The latency that we're trying to get to is around what? Is it in the microsecond range? Is it in the millisecond?
I come here in part to learn that, right? The answer is that I was talking to Dave and Victor on my last visit to Microsoft, and Victor, you had a millisecond application, right? The character recognition.
Yeah, so, right.
I mean-
It's not character recognition, actually, if you want to do anything with touch, so even if you have like 5 milliseconds, it's actually turn on, because you actually see, like, if you're drawing a pen, you'll see a lag, and that's completely unacceptable. So, of course, that's the edge of all that stuff. It's not probably going to get there, but in theory, if you kind of get there, that would be sort of the ultimate in some sense. I think that's what I was saying to you.
Yeah. I think that's, I mean, if you're doing this case, one of my favorites is, the favorite application I have not yet done is to do 360-degree shared streaming VR to people over mobile phones. And the idea is to do it in a pair of HTML5 streams, 360 by 180, right? So full stereoscopic view. So I can do this and get a full wraparound view. With a single guide. There's actually use cases for that, at least educational use cases, and probably others as well. And for that, for the receiver, the receiver doesn't get to pick doesn't get to pick where he is. So frankly there isn't. From his perspective, there probably isn't much of a latency constraint. From the perspective of the guide, right, who's picking the point of view that everybody's looking at, the latency constraint would likely be on the order of milliseconds, for example, right? But there's only one real way to find out, and that's to user test. Like the 150 millisecond end-to-end I got from Dave Anderson at CMU, who did studies on this in the early 2000s.
Okay, so because we are sort of behind schedule and people have to leave, so at this point I'll just thank the speaker one more time. And,